Assalamu alaikum warahmatullahi wabarakatuh, everybody. Welcome to continue our course Microcontrolling Start as Professional. We are in Module 6. In part 1 of Module 6 we spoke about assembly in general, and now in part 2 we are going to cover how to apply basic input-output operations in assembly language. To understand the input-output, we should know that microcontrollers, and AVR is one of them, actually has many built-in capabilities that can do a variety of input-output tasks. The lists include digital input-output, analog input, and this analog input usually is connected to an ADC, analog to digital converter. The timers can be considered as input-output devices, and we have the serial communication, which also used to send bits and receive bits from other devices bit by bit serially. If you want to connect any external device to your microcontroller, you should use the ports. Atmega 32 that we are studying in this course has digital input-output ports. Also it have analog to digital input port. Also it supports the serial communication through serial port. The number of ports depends on the processor type. So each port has a specific fixed addresses in the I/O address space. This address is actually to control the ports. So each port, as we will see later, has 3 registers to control this port. How can we access the ports? We use, as I said, the special input-output instruction that use special input-output addresses. These memory locations are the registers of input-output. As you can see here, as you know, we have 2 memories. So one memory is separated and it's only for the program. It's called the program memory, and we have the data memory. The upper part of the data memory is the general purpose working register. Next, 64 places in the memory are allocated for the input-output registers. Of course, here we are speaking about AVR Atmega 32. Okay. Then comes the internal data memory, which is SRAM, and you can attach to it an external SRAM. So as you see, the addresses for general purpose registers is between 0 and 1F, which are 31, and after that 20 hexadecimal to 5F are the places for the input-output registers. If we look to the data sheet of Atmega 32, so can you see here? So this address is between R0 to R31 occupy the addresses of the memory between 0000 up to 001F. After them come the I/O registers, then the memory. To access the input-output ports, Atmega 32 use special instructions which are in and out. So the I/O location are accessed by the in and out instruction, transferring data between the 32 general purpose register and the I/O space. As we said, the CPU cannot access directly to the memory. It's only access to the general purpose register. So to use data, we need to use the general purpose registers as a median between the processor and the ports. If we use the specific commands in and out, we can use the addresses between 0 to 3F. So going back to here, so this, if we use in, we can consider the first address, which is 20 as 0, and here is the 64. Okay, so the addresses are between 0 and 3F. If we use the LDS and STS, then we use the real addresses. So we use, instead of 00, 20. So we add 20 here and 20 here. So the address became between 20 and 5F. So between 20 and 5F. But this if we use LDS and STS. But if we want to use in out, so in 0, actually we access the place which is 20 in the memory. If we look at the data sheet, you see this is the addresses. So port A have the address 1B or 3B. So the Atmega 32 has 4 digital I/O ports: port A, port B, port C, port D, as we see here. Okay, so these 4 ports, each one of them has 3 registers to control it. So each of these ports is associated with 3 special purpose registers. The register at address hexadecimal 17 is the DDR B. Okay, each pin can be configured independently. So this DDRB is to configure the input output. So if it's set to 0, that means this pin is input. If it's set to 1, that means this pin is output. As you see here, actually the boards, everything is inside this chip, so actually we access them through this pin. So to decide the direction, if this pin is input or output, we need the register DDRB. Then writing to a board, we don't write directly to the pin. Of course there is a register, we write to it, and this register is connected to the pin. So if you want to take the value, if it's 0 or 1, you take it from this register. So the out instruction is used to write value from a register to board. Okay, so out is out. What is on the register? On the register which address 18, which is the memory 18, which is the memory inside the general memory, and this place is associated with the output. Okay, reading from the board we use in, and this time reading from a place to a register. Okay, now the address of these ports: for port A is 1B, DDRA is 1A, and BNA is 19. So this is for output, this for input. So when we read data through the pins, it's stored in this register. When we want to put data on the pins, we put it on this register, and this register is for the direction, input or output. For Atmega 328, it has only 3 ports, which are D, C, and B, and they have different addresses. So each microcontroller you are going to use have different addresses for its port. As you see here, this is Atmega 328. It has less number of pins and consequently less number of ports, 3 ports only, and this one have 4 ports, which is Mega 32. To solve this problem, not to remember all the addresses for each controller, and every time we need to write to a board or read from a board we need to go to the data sheet, we can actually use the libraries. So if we include the library M32A def.inc, this includes a lot of data. So now instead of writing the address, we can just include the library and write DDRA and board A and BNA. This will replace by the address 19. DDR is replaced by the address 1A. It's not 19, 19 and 1A because it's hexadecimal. Okay, so this is how we can make benefit of the include file. No need to remember all the addresses. So next we will go to do some example in the next page of this module, but before that I want to explain another important concept that we need to use, which is called the floating state pull up and pull down resistors. Now the digital logic circuits have 3 logic states. We know 2 of them, which is 1 and low, and the third one is called the floating state or the high impedance states or the Z state, which is not 0, not 1. In this case, the pin is not connected to 0, that means it's not grounded and not supplied with 5 volts. So we cannot exactly know what will be the value of this pin. So in this case, we call it its floating, is unconnected input pin of the microcontroller. So it's unconnected, it's floating, so it's a high impedance. We don't know really if it's 1 or 0. Usually when we work with microcontroller, we need to make sure that the value is even 0 or on. So we can choose pull up or pull down resistor to choose the initial case. Pull up, pull down resistor are used to solve the dilemma for the microcontroller by pulling the value of the logical high or logical low state. So this is pull up resistor. Usually the buttons is connected like this. So if we want to give 0, we just push the button. So now the pin is grounded and the voltage here is 0. If we release the button, it's not connected, so now it's 1. For pull down, it's always 0 unless we push the button. So when we push the button, we give voltage here, so the voltage drop here is 5 volt. So like this, we guarantee in pull up resistor it's always 5 volt unless we push the button. For pull down resistor it's always 0 unless we push the button. Actually, no need to always to build this circuit. There is what's called the built-in pull-up resistors. So instead of using the hardware pull up resistor and pull down resistor, some microcontrollers have a built-in pull up resistors. When we set the DDR of any port A, B, C or D to 0, we make the port pin as inputs. That means we put the port as inputs, then the corresponding bit in the defined port register are used to activate deactivate pull up registers associated with the pin. So in order to activate pull up resistor, we set port A or port B, C, D. If we set A, for example, to 1, that means we are activating the pull up resistors. So you will understand this in more details later when we go to solve the example or show the examples. For now, this is all what I want to cover in this part. Thank you for listening, and let's move to see the example how we can apply some assembly language codes on our microcontroller and see the effects on the output ports using the LED. Thank you for listening and have a nice day.